In this video, we're going to introduce what a limit is and talk about how we do a limit numerically. So I want to motivate this with an example. So let's say that we have the function f of x, which is x cubed minus 8 over x minus 2. So what is f of 2? Well, if we plug 2 into this, we get 2 cubed minus 8 on the top, 2 minus 2 on the bottom, and then 2 cubed is 8. So we have 0 on the top, and 2 minus 2 is 0 on the bottom. And 0 over 0, that is undefined. 0 over 0 is undefined. We cannot divide by 0 no matter what we have on the top. So a question that I want to ask is, well, I can't plug 2 into this, but what happens to the function, to f of x? So specifically, what happens to its y values as x gets close to 2? Because exactly at 2, we have a problem. It's undefined because the denominator is 0. But what's happening close to 2? As x gets close to 2, what will happen to f of x? So to answer this, let's look at a table of values. A table of values. Let's make a table where we keep track of what x is and what f of x is. This is the output. So the output is the y value. Let me zoom out a little bit so I can keep track of this. Oops, sorry. Okay, so I need to plug in some numbers for x that get closer and closer to 2. So maybe let me start off by plugging in 2.1 in for x. I went ahead and did this already with a calculator ahead of time, so I'm just going to tell you what it is. So if we plug that into our function, and here was our function, we end up with 12.61. Okay, so let's plug in something even closer to 2, like 2.01. If we plug that in, we get 12.0601. Now let me write that a little bit better. 0601. And now so at this point it seems like maybe f of x is getting really close to 12. So let's just try plugging another x value that's even closer, like 2.001. And if we do that, then we get 12.006. So at this point, we really think that it might be getting close to 12. But so far, every x value that I've plugged in has been bigger than 2. Maybe something different happens when I plug in things that are smaller than 2. Well, that's conceivable, it could. So let's try plugging in something smaller than 2, like 1.9. And then I'll get even closer, like 1.99. And then even closer, like 1.999. It turns out if you plug in 1.9, we get 11.41. And plugging in 1.99, we get 11.9401. So getting closer to 12. And 1.999, plug that in, we get 11.994. So from either side of 2, this is sort of all the numbers bigger than 2. These are some numbers smaller than 2. It seems like their corresponding y values, what f of x is getting closer and closer to 2. So I'm going to write that down. It seems like as x approaches 2, f of x, and f of x refers to the y values. F of x refers to the output, the y values. It seems like f of x approaches 12. So we have a notation to express this concept of, oh, as x gets really close to a number, what do the y values get close to? And the notation is the following. So I have this lim. Underneath that, I have x and an arrow pointing to 2. F of x written here, and then equals 12. Okay, and the way I say this in words is I write the limit of f of x, of my function, as x approaches 2 is 12. That's how I would say this notation in words. It's saying as x gets really, really close to 2, f of x the y values, are getting really close to 12. So the question now is, are we sure that the limit is 12? Because we just have a table of values. We just plugged in, a few values. So the answer is technically no. We're not absolutely sure. We would need to plug in more values. We would need to plug in x values that get closer and closer to 2, and we'd have to do this forever. Okay, and we just don't have time for that. So I'm going to put a sad face here. But luckily, there are other ways to evaluate a limit rather than relying on a table of values like this that can lead to us knowing for sure what the limit is. So there are 2 ways I'm going to list that we can know a little bit more definitively. So the first is to evaluate the limit graphically. And that we are going to talk about more in the next video. We'll preview it a little bit in this video actually, but we'll talk about it a lot more detail in the next video. And the second way is algebraically. Okay, and that we will talk about in a later section. Section 3.3 is all about evaluating limits algebraically. But either of those ways can lead us knowing more definitively what the limit is. Okay, so what I want to do now is I want to graph this function. Let's graph our function to see, well, what is the limit? Okay, so I went ahead, so I'm actually just going to tell you what the graph looks like. Okay, so I've actually already drawn in the y-axis here. So let me draw in an x-axis. So let's draw in an x-axis. Then I'll put some tick marks. So I'll go -1, -2, -3 in the x direction, and 1 in the x direction, 2 in the y direction. I actually won't really put tick marks in the, this is 1 and 2 in the positive x direction, I meant to say. I won't put in any tick marks on the y-axis because the points grow, they get really, really high quickly. So that's why I won't put any tick marks on the y-axis. Instead, I'll just draw the general shape. So it turns out that the graph will have a point at -1, 3, and then it sort of looks like a parabola going up this way. In fact, it also looks like a parabola going up this way. But the thing is, when I get to 2, when x equals 2, I have an undefined thing going on. So I have to sort of skip what happens there. And the way I sort of skip it is I put a hole, and it turns out the y value of this hole is 12, which is what the limit was. And then the graph sort of continues beyond that. Okay, so this graph has a hole at the point 2, 12, it turns out. And when we talk about the limit, we just care about what's happening as x gets really close to 2. So as x gets really, really close to 2 from this side, and really, really close to 2 from this side, and that's here on the graph, this part of the graph, and it's also this part of the graph. And as x gets really, really close to 2, the y values seem to get really, really close to 12. And it doesn't matter that there's a hole right at that point, because we don't care what's happening right at 2, just what's happening really close to 2. Because we already know that we can't plug 2 into this. That's why we're just plugging in things really, really close to it. But it seems reasonable now, looking at this graph, that the limit is 12 as x gets close to 2. Okay, so now we are ready to state the definition of a limit a little bit more technically, just defining it. Okay, so I have this written down. I'm going to read through it, and then we'll talk about it a bit. So we say that the limit of f of x as x approaches a equals a number L. And this is what it looks like with our notation. We write it as a limit. Underneath that, we put x, an arrow going to a. That means x is getting really close to a. F of x is our function, and then we write that it equals L. So we're defining what it means for the limit to be equal to L. So we say that happens if as x gets closer and closer to a, whatever number a is, but not equal to a. That is super important. The fact that we don't care about what's happening when x actually equals a. So as that happens, we need f of x to get closer and closer to this number L. And L in this is a single, so that means it's exactly one, finite number. So we can't have a situation where like our function is getting close to 3 different numbers. That would be bad. It's got to be getting close to just one, just a single finite number. And if that happens, we say that the limit as x approaches a of f of x equals L. So if, on the other hand, f of x does not approach just one finite number as x approaches a, and there's sort of 2 important parts to that. There's the either it doesn't approach just one, and the other part is the finiteness. So if it doesn't approach a finite thing, that would be bad. So if that doesn't happen as x gets close to a, then we say that the limit of f of x as x approaches a does not exist. Or for short, we will write d and e. So what I want to end this video now is by describing some pictures of what a limit not existing would look like. Actually, before I do that, in this picture right here, the limit does exist. So the limit as x approaches, 2 of f of x does exist. It exists. And what it means for it to exist is it equals a finite number. So what does it equal? It equals 12. That's what the y values are getting really, really close to. So what would a graph look like for the limit not to exist? That's what I want to end the video by drawing. Okay, so there's a few different ways this could look. Okay, so I'm going to draw a few different pictures. Okay, so I'm going to draw some axes here. I'm going to draw some axes here in the middle as well, and some axes over here. I'm going to draw three different graphs actually. Okay, so in this first graph, let's say that this is 1, and as we get close to 1 from maybe this side, maybe the y values are getting super, super close to 5. And as you get close to 1 from the other side, maybe the y values are getting close to 3. Okay, so in this picture right here, let me scroll down a little bit, the limit as x approaches 1 of f of x does not exist. So I'll write d and e, it does not exist. Well, let's talk about why. Okay, so I need to write a little bit, let's just zoom out. This limit does not exist. So what is the reason? So the reason here is that as x approaches 1, and this is how I write it symbolically, I write x, I put an arrow going to 1, and that means x is getting closer and closer to 1. F of x, and when I write f of x, I'm talking about the y values, f of x approaches 2 values. There are 2 numbers that f of x, that our y values, seem to be getting close to. And those 2 numbers seem to be 5 and 3, depending on which side we're getting really, really close to x equals 1 from. So there are 2 values f of x is approaching, not 1. And that's bad, because the definition of a limit being equal to a number says that f of x needs to get closer and closer to L, where L is just a single finite number. Okay, so that's why this limit doesn't exist in this picture. The y values seem to be getting close to 2 different numbers, 5 and 3. Okay, what's another way a limit could not exist? Well, if I have a scenario where there is like a vertical asymptote, because with a vertical asymptote, the graph would either be going to infinity or negative infinity, and for a limit to exist, it's got to be a finite number. And a vertical asymptote is associated with some sort of infiniteness. So let me just draw one example of a picture with a vertical asymptote, although there could be many ways this could look. Let's say that it goes up towards the vertical asymptote here. And maybe on the other side as well, it goes up towards the vertical asymptote. even if it were to go down towards the vertical asymptote, it would still be an infinite type situation, and that's not what falls in the realm of the limit existing. So here the limit as x gets close to -2 of our function does not exist, so dne. And what's the reason? Oh, let's put this in green again. So reason. The reason is as x approaches -2, f of x, so our y values, we got to think about what they're approaching. F of x, in this case, does not approach a finite number. Because it seems like as x gets really, really close to -2 on the graph, the y values seem to get infinitely large. But for the limit to exist, the y values are supposed to get close to a single finite number. And here they're not approaching a finite number at all. That's why the limit doesn't exist. Okay, so I'm going to introduce a more precise way to write this. It turns out that we will actually write in a situation like this, that the limit as x approaches -2 of our function equals infinity. So when we can be more specific about a d and e limit, so if the y values are getting really, really big, infinitely big like this, we will be more specific. In this case, I will say that the limit is infinity. That means the y values are getting infinitely large. Okay, which means, so let me just describe what this means. This means two things. On one hand, it means that the limit as x approaches -2 of our function does not exist, dne, but it means a little bit more than that. And it also means, second condition, that the y values are getting infinitely large. So if I do have a limit like this, that's dne, but I can be more specific, like if the y values are getting infinitely large, I should specify that and say, oh, the limit is actually infinity, which an infinity falls into the dne category because it's not finite, but I want to be more specific. In the same way, even if my graph had been going to negative infinity on sort of both sides, I would have specified that the limit is negative infinity. Okay, one more type of picture for a dne limit that I want to show in this video, and that's if, so I'm actually going to give a specific function example here, and the function is sine of 1 over x. Okay, and in our class in Math 30 and Math 31, we actually don't talk about trig functions at all, but I want to briefly just mention this here to show that there is another way a limit doesn't exist, and it happens to occur with this specific function. Okay, so what happens with sine of 1 over x is, just like the graph of sine, it sort of oscillates up and down, but as you get closer and closer to 0, like if you try to plug 0 into this, you get 1 over 0, which is undefined. And graphically what happens is the graph starts to oscillate faster and faster and faster the closer you get to 0. And it starts to get faster and faster and faster and faster. Okay, same thing from the other side. From the other side, it starts off slow, but the closer and closer and closer to 0 get, the faster it oscillates. So this limit, the limit as x approaches 0 of f of x in this graph, also does not exist. This also does not exist, but there must be a reason, just like there were with other two graphs. So what is the reason here? Okay, so let's zoom out a bit, and let's write down this reason. So the reason here is, now x is approaching 0. As x approaches 0, f of x, what is f of x approaching? What are our y values approaching? Well, because of this like infinite type of oscillation that's happening, f of x approaches every number in -1 to 1 in some sense. It keeps it keeps hitting every number in the interval from -1 to +1, because it keeps going down to -1, up to +1, again and again and again, infinite number of times. And that's bad. That the limit, the y values are not just getting close to one finite number. That's why the limit doesn't exist in this picture. All right, so with regards to our goals, we've talked about how we've introduced what a limit is, and how we can find a limit numerically using a table of values. And we've briefly just introed graphically what that looks like, but we'll discuss it in a lot more detail and do a lot more examples in the next video.